Okay, so okay, like I mentioned, so this is the course on foundations of cognitive robotics, and I am Suryadeep, the TA, and this is the course offered by Professor Bishak Bhattacharya from IIT Kanpur. Okay, this QR code takes you to the link of the actual course where you can find the relevant materials for this year. Okay, so I'll be discussing the questions from previous year, and I have taken 9 questions from previous year's week 1 assignment, and I'll discuss them, and I'll give some hints and some side notes as well, as much as I can, to help you with your understanding. Okay, so let's start with the first question. Yeah, so what is the Turing test concerned with? This is the first question. So you have 4 options. The first one is determining whether a robot is capable of thinking like a human, determining the degrees of freedom, determining the agility of the robot, or ensuring fast, safe working environment for robot. So now among these 4, the correct answer is determining whether a robot is capable of thinking like a human being. So the Turing test, also known as the imitation game, so it was the term Turing test was coined later on. Alan Turing in 1950 used the term imitation game, where he meant that where he wanted to ask this question whether a machine or a robot can think like a human being or not. So can it imitate a human being? Hence the name imitation game, and hence the name of the movie on Alan Turing as well. So here what we do is there is a human evaluator, and there is a robot and a human being, and they interact through via text only, no speech, and the evaluator has to distinguish who is the human being and who is the robot. And if it cannot satisfactorily distinguish between the human and the robot, in that case the robot is said to have passed the Turing test. So that was the Turing test. Okay, if you have any question regarding that, you can type it in the chat box, and I'll have a look at it at the end of it. So wait, I think some people are waiting to join the session. Just let me check. Okay, okay, I think people have joined. Okay, I can go back to the presentation. Okay, this was the Turing test. Second question, or rather the third one from the assignment, is which of the following is false about electroactive polymers? So electroactive polymers are basically polymers whose shape and size change when applied with an electric field. So there are different types of electroactive polymers. One of them is the ionic polymers. So these are the 4 options. It requires low driving voltage, slow response time, performs better under wet conditions, and high energy density. Now which among these 4 is false? So the right answer is high energy density, because ionic electroactive polymers do not require high energy density, but the rest all 3 are true. They require low driving voltage, that is to actuate the polymer. They have slow response time, performs better under wet conditions. So the right answer is D. Coming to the 4th question, what is the shape memory effect? Shape memory effect is defined as, we have 4 options. The first one is the actuation behavior of a shape memory alloy. SMA stands for shape memory alloy, caused due to formation of stress induced martensite from austenite phase at constant temperature, or recovery of strains imparted on a SMA at a certain temperature upon stress application, recovery of strains imparted on a SMA at a lower temperature as a result of thermal activation. The actuation behavior of a SMA caused due to formation of stress induced austenite from martensite phase at constant temperature. So what is the shape memory effect? Shape memory effect is basically it whenever the smart material is its shape is changed, it can remember what its original shape was and it can go back to that shape. For shape memory effects specifically deals with this option C, where if a shape memory alloy is heated at a low temperature, it gets deformed, but when it's cooled, it again gets back to its original shape. So there can be two ways of shape memory effect. One is either through heating and it returns to its shape, or it can happen both way. If you heat, it remembers both the shapes, shape when it is heated and the shape when it is cooled, and it can interchange depending on the temperature. So the right answer over here is C. Okay, moving on to the next question. Which one of the following is the correct actuator constitutive equation for a magnetostrictive material? So you have 4 equations over here, and the correct answer is D, where epsilon is the strain, sigma is the stress, S to the power h, the on superscript h is the compliance matrix of the material at constant magnetic intensity, and h is the magnetic intensity. So this is the actuator equation for a magnetostrictive material. What is a magnetostrictive material? It is a material which when under a magnetic field, and if you pass electric if you is a material through which if you pass helical magnetic field through an electric coil like a solenoid, it generates stress within the material and leads to torques within it twists basically. So those type of materials, smart materials, are called magnetostrictive materials. So the right answer here is D. Moving on, so coming to the 6th question. Helical magnetic field producing torque in a magnetostrictive material is known as, you have 4 options: magneto-volume effect, Villari effect, Matteucci effect, and the Weidemann effect. So among this, so like I said, a magnetostrictive material, what is a helical magnetic field is produced by a solenoid coil, like if you wrap a electric coil around it, so it will produce the helical magnetic field, and that in turn produces torque. This effect is known as the Weidemann effect. This is the direct effect, and there is a thermodynamically inverse effect of it, which is the Matteucci effect. So what happens there is, if you take a magnetostrictive material and if you twist it, if you keep it under a magnetic field and twist it, it generates an electric field. So that is known as the Matteucci effect. It's the inverse of the Weidemann effect. And the right answer for this question is option D. Okay, I think some people are waiting. Let me check once again. Okay. Okay, let me go back to the presentation. Yeah. Okay, coming to question 7. So the input and output of direct piezoelectric effect are respectively, you have 4 options: electric stimulus and strain, stress and change in electric potential, stress and pressure, stress and change in magnetization. So the direct piezoelectric effect is basically you apply stress and you generate electricity. So the option is B, where you apply stress and you get an electric potential which you can connect to a circuit and generate electricity. However, there is also a converse piezoelectric effect, which is basically what you do is you apply electric stimulus to the piezoelectric material, and as a result that material changes its shape or a strain is produced. So this is the converse. So the right answer for this question is B. Coming to question 8, which of the following does not fall under category of smart materials? So you have 4 options: magnetostrictive material, shape memory alloy, carbon fiber, and electrorheological materials. So I'll discuss what all 4 of them are. So a magnetostrictive material is basically you apply electric field to a material and generate a magnetic field around that material, and it changes shape, so it twists basically. So these are magnetostrictive material. A shape memory alloy is if you heat it, it changes shape and it can go back to its previous shape when cooled. Electrorheological materials, when applied electricity, the viscosity of the material changes, so the fluid properties of the material changes. So these are now coming to carbon fiber. So if you apply any external stimuli, so nothing really happens in that case. So this does not fall under the category of smart material. The right answer over here is carbon fiber. Now what are smart materials? Are basically are materials that you can control and manipulate. You can make them respond in a certain way on applying external stimulus. Basically you can convert one form of energy to the other for certain materials. Those are the smart materials. Like in magnetostrictive, you convert electric energy to mechanical energy. Shape memory alloy, thermal energy to mechanical energy. In electrorheological materials, you convert again electric energy to mechanical energy, or whatever purpose you are using it for. But carbon fiber, if you apply any electric field or you cannot get back any output, any desired output. So this does not fall into the category of smart materials. So the right answer is C. Okay, okay, I think okay. Okay, coming to question number 9 is what is the Nagaoka Honda effect associated with. So you have 4 options: generation of torque due to helical magnetic field, generation of charge due to applied stress, change in magnetic state due to change in volume, generation of force due to electric field. So the right answer is C, where the magnetic state changes when the shape or the volume of the material changes. This is an inverse effect of a magnetostrictive material. So when you change the volume, if you apply stress or strain on the material, its volume changes. As a result, its magnetic state changes. So this is known as the Nagaoka Honda effect. So the right answer over here is C. Okay, so coming to the final question of our discussion today. So which of the following soft smart materials will be most suitable to operate in a bandwidth of 0.1 Hz to 1 GHz? So you have 4 materials. So first one is terphenol D, next one is nitinol, third one is PVDF, and the fourth one is galphenol. Now I'll discuss what type of materials each 4 of them are. So terphenol D is a magnetostrictive material, where nitinol happens to be a shape memory alloy. PVDF happens to be a piezoelectric material, and galphenol happens to be a magnetostrictive material again. Now you see the range of frequency, which is very high, a very wide range from 0.1 hertz to 1 gigahertz. That's a wide range. So most of these materials do not operate at such a wide range of frequency. Only piezoelectric materials can work, are most suitable to work rather at such a high frequency range. So the right answer is PVDF. So terphenol D is magnetostrictive, nitinol is shape memory alloy, PVDF is a piezoelectric material, and galphenol happens to be a magnetostrictive material. Galphenol is basically used in sonars to detect sounds underwater in submarines. Nitinol is a shape memory alloy that is the most commonly available commercially in the market. So these were the questions that we discussed today. So now if you have any question, so please write it in the comments, and regarding the questions that were discussed, and I'll try to answer them as best as I can. So let me go open the chat box. Okay, so if you have any questions in the chat box, please type them now. And okay, so the we discussed, basically the idea was to discuss previous year's questions so as to give you an idea so that you can solve this year's question. So this year's questions I intentionally did not take up in this assignment because it's for you to solve, and you can find some overlap between the assignments, but most of the questions in this year are quite different from what I have presented here. Oh, okay, then I think if you do not have any questions, we can close the session for today, and we can meet again next week, and I'll discuss the week 2's assignment in the upcoming week. So one final check at the comments. I think no one has. Okay, so thank you everyone for taking the time to come to this session. I wish you all the best for the course, and see you again next week. Thank you.